A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
You know, Corn, this whole show runs on GPU compute, and we wouldn't be here without Modal.
Seriously. And that's what powers all our text-to-speech. Everything you're hearing right now.
They're an AI infrastructure platform. Developers use them to run GPU workloads in the cloud with zero infrastructure headaches.
If you're building anything with AI, check them out. Modal.com. So Daniel sent us this one. And it's a topic that I think a lot of people building AI systems right now need to hear. He's pointing us at a landmark Google DeepMind and MIT study called Towards the Science of Scaling Agent Systems, and the finding is genuinely counterintuitive. Adding more agents to a system is about as likely to hurt performance as help it. The paper tested 260 configurations across 6 benchmarks, and the numbers are striking. Independent agents amplify errors 17 times compared to a single agent. Every multi-agent variant tested degraded sequential reasoning by 39 to 70%, and the token cost runs 1.6 to 6 times higher for matched performance. Daniel's asking what this means for the whole vision of autonomous agent swarms, and whether we're actually heading toward a future of small, curated agent teams rather than large-scale agent societies. Lots to dig into here.
Herman Poppleberry, by the way, for anyone new. And, yeah, this is one of those papers where the findings feel obvious in retrospect, but run completely against how the industry has been building for the last 2 years.
The whole pitch has been additive, right? More agents, more specialization, better coverage. It's basically the engineering instinct applied to AI.
And that instinct comes from somewhere real. Microservices, human teams, parallel compute, decomposition works in a lot of contexts. The problem is that agents aren't microservices, and the research is now showing us exactly why in quantitative terms. By the way, today's script is courtesy of Claude Sonnet 4.6, our AI collaborator down the road.
So let's start with the 17.2 times error amplification number, because that's the one that jumped out at me. What's actually happening there mechanically?
So the study tested 5 canonical architectures. Single agent, one model with a unified memory stream. Independent, multiple agents running in parallel with no communication, results aggregated at the end. Centralized hub and spoke, an orchestrator delegates to workers and synthesizes outputs. Decentralized, peer-to-peer mesh, agents communicate directly. And hybrid, hierarchical oversight combined with peer-to-peer coordination. The independent architecture is the one hitting 17.2 times error amplification, and the mechanism is straightforward once you see it. Each agent runs without visibility into what the others are doing, so when one agent makes an error, there's no correction signal. The aggregation step at the end doesn't fix errors. It averages them, or in the worst case, it amplifies the wrong answer because multiple agents independently converged on the same mistake.
So you're not getting independent verification, you're getting correlated failures.
That's the key insight. If the agents share the same underlying model, they share the same failure modes. They'll make the same mistakes on the same inputs. So independent doesn't mean independent in any meaningful statistical sense. It means you've multiplied your failure surface without adding any genuine diversity. The centralized architecture does better, 4.4 times amplification rather than 17, because the orchestrator acts as what the paper calls a validation bottleneck. It catches errors before they propagate downstream. But even 4.4 times is not a great number.
And then on sequential tasks, it gets worse. The 39 to 70% degradation figure, that's for every multi-agent variant, not just the independent one.
Every single one. That's what makes the sequential task finding so significant. The study used a benchmark called PlanCraft, which is planning in a Minecraft environment. The reason it's strictly sequential is that each action changes the inventory that later actions depend on. You can't parallelize that. The state of the world at step 8 depends on what happened at steps 1 through 7. And when you fragment that reasoning across multiple agents, you're essentially forcing each agent to reconstruct context that the previous agent already had. That reconstruction is lossy. The paper quantifies the token cost of that reconstruction. 37% of total tokens in multi-agent systems are what they call coordination tokens, paying to reestablish shared state rather than doing actual work.
37% of your token budget is just overhead. That's extraordinary when you say it plainly.
And it compounds. The paper's token efficiency numbers are stark. Single agent, 67 tasks per 1,000 tokens. Centralized multi-agent, 21 tasks per 1,000 tokens. Hybrid, 14 tasks per 1,000 tokens. So you're paying 3 to 5 times more per unit of work. There's a production case study from a document analysis workflow. 3-agent pipeline running $47,000 a month. Refactored single-agent version running $22,700. The accuracy difference was 2.1 percentage points. The team spent 3 months building the pipeline before anyone measured it against a baseline.
That's a painful paragraph to read if you've just spent 3 months building a pipeline.
The engineering blog that reported it put it bluntly. Start with one agent, measure it honestly, and add coordination only when the data says you need it, which is obvious advice in hindsight, but the organizational pressures run the other direction.
Say more about that because I think this is underappreciated. There's a social dynamic here that the research doesn't fully capture.
The organizational pressure toward complexity is real and it's structural. A 5-agent pipeline with the supervisor and a critic layer sounds sophisticated in a design review. We have a single agent. Sounds naive, like you haven't thought hard about the problem. Framework vendors have built their entire value proposition around orchestration as a differentiator. LangGraph, AutoGen, Crew AI. Their business model is multi-agent coordination, so there's a whole ecosystem of incentives pushing practitioners toward architectural complexity before they've measured whether they need it.
It's the microservices era of AI, essentially. Everyone built microservices because it was the sophisticated thing to do. And then a decade later, people started writing. Maybe a monolith was fine, actually. Blog posts.
The parallel is pretty direct. And the paper from Tianpan.co makes exactly that point. Specialization as an architectural strategy is running against the direction of model development, not with it. The single capable agent of today is broadly more capable than the 3-agent pipeline of 2 years ago. As foundation models improve, the set of tasks where multi-agent coordination actually outperforms a capable single agent keeps shrinking.
Which brings us to the capability saturation finding, which I want to spend some time on because it's the most practically useful result in the paper.
The capability saturation effect, the paper calls it a threshold around 45% single agent accuracy. Once your single agent is hitting roughly 45% on a task, adding more agents yields diminishing or negative returns. Below that threshold, multi-agent coordination can genuinely help. It's essentially compensating for model weakness. Above it, the coordination overhead starts to dominate. The theoretical implication is significant. Multi-agent coordination is a workaround for capability gaps, not a permanent architectural advantage.
So the right question before you architect a multi-agent system is not, how do I decompose this task? It's what does my single agent baseline actually score?
That's the 45% rule as an engineering heuristic. Measure first. Most teams aren't doing this. They're reaching for multi-agent complexity before establishing what a single capable agent can do. The paper found that their predictive model, which uses measurable task properties like tool count, decomposability, and sequential dependencies, correctly identifies the optimal coordination strategy for 87% of unseen configurations. That's a genuinely useful result because it suggests we're moving toward principled agent design rather than guesswork.
Okay, but let's steelman the multi-agent case, because it's not all bad news. The paper does find an 80% improvement on parallelizable tasks.
The alignment principle is real and the numbers are large. On Finance Agent, which is a financial reasoning benchmark with highly parallelizable subtasks, one agent analyzing revenue trends, another analyzing cost structures, another looking at market comparisons, centralized coordination improved performance by 80.8% over single agent. That's a genuine substantial gain. The key is that the subtasks are truly independent. The revenue analysis doesn't depend on the cost analysis being done first. When you can decompose a problem into genuinely non-overlapping work streams, parallel agents shine.
And the SWE bench coding result is interesting too. That's a real gain on a real benchmark.
The coding case is instructive because of why it works. A multi-agent team, manager, researcher, engineer, reviewer hit 72.2% on SWE bench verified compared to 65% for a solo agent. 7.2 percentage points is meaningful. But the reason it works in code is that code has an objective verification signal. Tests either pass or fail. That gives the reviewer agent grounded feedback. It's not just arguing about the quality of reasoning, it's running the tests and reporting concrete results. The adversarial review pattern works when you have objective signals to anchor it.
Compare that to multi-agent debate, which is the more general pattern, and the results are much weaker.
The ICLR 2025 evaluation of multi-agent debate frameworks is blunt. They tested 5 frameworks, the original Do et al. MAD framework, multi-persona, exchange of thoughts, chat eval, and agent verse, across 9 benchmarks using GPT-4o Mini and Llama 3.18 billion. The verdict, current MAD frameworks fail to consistently outperform simple single-agent test time computation strategies. Most can't beat chain-of-thought prompting. Most can't beat self-consistency, which just resamples from the same single agent multiple times. Increasing agent count or debate rounds does not reliably improve performance.
Self-consistency beating a multi-agent debate system is a pretty damning result. You're literally just running the same model more times.
And it makes sense once you understand the failure mode. The evaluation found that MAD methods are overly aggressive. They turn correct answers into incorrect ones at a higher rate than they fix wrong answers. The multi-persona framework is the worst offender because the devil's advocate agent has a structural mandate to oppose, regardless of whether the original answer was right. You've built in a mechanism that degrades correct reasoning.
There's a finding from the MAS paper, the Berkeley Forensic Analysis, that connects here. They built a taxonomy of why multi-agent systems fail, and the failure modes cluster around coordination, not capability.
The MAS paper is fascinating as a forensic document. They collected over 1,600 annotated failure traces across 7 popular multi-agent frameworks and identified 14 distinct failure modes in 3 categories. System design issues. Problems baked in at architecture time. Inter-agent misalignment, coordination failures, including things like conversation reset, task derailment, information withholding, and one they call ignored other agents' input, which is exactly what it sounds like. And task verification failures. The system doesn't check its own outputs adequately. The inter-annotator agreement was 0.88 kappa, which is high. These failure modes are real and identifiable, not noise. And the finding is that most failures aren't. The model wasn't smart enough. They're coordination and communication failures.
Which brings up the topology question, because not all multi-agent architectures are equally bad at coordination.
The McNett paper from Tsinghua is the most optimistic of the studies, and it's worth taking seriously because it identifies where structure actually matters. McNett organizes agents into directed acyclic graphs rather than fixed topologies. The key finding is that irregular topologies outperform regular ones. Fixed symmetric structures, rings, grids, star patterns, perform worse than adaptive irregular ones. And the intuition makes sense. Irregular topologies allow information to flow along paths that match the actual dependency structure of the task. If your task has a specific dependency graph, step A must precede step B, but step C is independent of both. Your communication topology should reflect that. Forcing information through a fixed grid means some of it travels through unnecessary hops.
So the right multi-agent architecture isn't a pattern you can pick off a shelf. It's something you derive from the task structure.
That's the practical implication. And it connects to the predictive model in the DeepMind paper. The task properties that predict optimal architecture are tool count, decomposability, and sequential dependency structure. If you map those properties for your specific task, you can derive the right topology rather than defaulting to whatever the framework's default configuration is. The McNett paper also identifies a collaborative scaling law. Performance follows a logistic growth curve as agents scale. Improvement up to a threshold, then plateau or decline. The sweet spot they identify is around 4 to 5 agents or 3 to 4 debate rounds before coordination overhead starts winning.
That logistic curve is interesting because it mirrors what we see in a lot of other scaling contexts. It's not that more is never better. It's that the curve has a ceiling that arrives faster than you'd expect.
The McNett paper makes a specific point about this. Collaborative emergence occurs earlier than traditional neural scaling emergence. Neural scaling intuitions from training compute suggest that gains compound over long ranges. Multi-agent collaboration hits its ceiling much faster. So if you're importing intuitions from bigger models keep getting better, those intuitions don't transfer cleanly to more agents keep getting better.
Let's talk about model diversity for a minute, because this is the finding that I think reframes the whole design question.
The MAD evaluation found that combining different foundation models, specifically GPT-4 Mini paired with Llama 3.170 billion, shows more promise than same. Model multi-agent debate. That's a significant result because it suggests the real variable isn't agent count, it's reasoning diversity. Two agents with genuinely different model architectures, training distributions, and failure modes can provide real error correction. 5 agents all running the same model are just expensive correlated sampling.
So the design question isn't how many agents, it's how different are the reasoning approaches in the system.
Which reframes the whole architecture conversation. If you're building a verification layer, the most valuable thing you can do is use a different foundation model for the critic than you used for the generator. Not because it's a larger model, but because its failure modes don't overlap. That's genuine independence in the statistical sense.
Where does this leave the broader vision of agent swarms? Because there's been a lot of investment and a lot of hype around the idea of emergent coordination at scale.
The research points towards something much more modest than swarms. Carefully curated small teams, 4 to 5 agents maximum, with explicit coordination protocols, clear task decomposition, and objective verification signals. The bag of agents approach, just throwing more agents at a problem, is what the Tianpan piece calls the multi-agent equivalent of hoping a bigger model will fix poor prompt engineering. It's the same category of mistake, substituting scale for design.
And the Gartner forecast from last June is looking increasingly well calibrated given all of this.
Over 40% of agentic AI projects canceled by end of 2027. The reasoning was escalating costs, unclear business value, and inadequate risk controls. That forecast was made before the full DeepMind findings were widely circulated, and the research now gives you the mechanistic explanation for why those projects will fail. The reliability compounding problem alone is a serious enterprise risk. At 97% per step reliability, which sounds high, a 10-step agentic workflow has a 74% end-to-end success rate. At 99.5% per step, you get 95% end-to-end. For enterprise deployments running millions of workflows, that gap is the difference between a reliable product and an unreliable one.
And I suspect most teams building these systems haven't actually measured their per-step reliability and done the compounding math.
Almost certainly not. The measurement culture in agentic AI is still immature. Teams are measuring benchmark performance on the overall task, not per-step reliability in their specific deployment environment. The mass paper's forensic approach, annotating failure traces, is the kind of methodology that production teams need to adopt, but it requires actually collecting and analyzing failure data, which most teams aren't set up to do.
So practically, what does a sensible decision framework look like for an engineer building agentic systems right now?
The research converges on a pretty clear decision tree. Start with a single agent. Measure it honestly on your specific task, not on a published benchmark, on your actual task. If your single agent baseline is already above 45% accuracy, adding agents is likely to cost more than it gains. If the task is primarily sequential, single agent wins. If the toolset fits in one context window, single agent wins. If your latency budget is under 5 seconds, single agent wins. The cases where multi-agent genuinely earns its complexity are narrower than the industry assumed. Demonstrably parallelizable subtasks with no ordering dependencies, objective verification signals that justify adversarial review, compliance requirements that mandate data isolation, or genuinely different foundation models in the critic and generator roles.
And the unified architecture results are worth flagging here because they're directly competitive with multi-agent systems on tasks that people assumed required orchestration.
Surfer 2, achieving 97.1% on Web Voyager using a unified architecture. OpenAI's deep research system outperforming prior multi-agent research pipelines as a single model optimized for web browsing and data analysis. These aren't cases where a single agent is good enough. They're cases where the unified architecture is actually better. The reasoning is that web navigation and research are fundamentally sequential. Each page you visit changes what you know, which changes what you look for next. Fragmenting that across agents doesn't help, it just creates coordination overhead on top of a task that was already hard.
I want to come back to something you said earlier about the direction of model development, because I think it's the most underappreciated point in this whole discussion.
The capability trajectory is working against the multi-agent value proposition over time. As foundation models improve, the tasks where a single capable agent falls short and where multi-agent coordination genuinely compensates keep shrinking. The 45% saturation threshold isn't a fixed number. As models get stronger, more tasks push above it. So, an architecture that made sense in 2024 when single agent performance on complex tasks was genuinely limited may not make sense now. The engineers who built those three-agent pipelines weren't wrong given what they knew. They were building with the tools available. The problem is that the tools improve faster than the architecture assumptions updated.
Which is actually a reasonable thing to have happened. The industry is learning in real time. The issue is the organizational inertia that keeps the old patterns in place after the evidence has moved.
The frameworks are already built, the teams are already trained on them, the design patterns are already documented. There's a switching cost to simplifying. And we're going to remove the orchestration layer and replace it with a single agent is a harder conversation to have than we're adding a new capability. Simplification requires admitting that the complexity you built wasn't necessary, which is a harder organizational move than adding more complexity.
All right, practical takeaways. What should someone listening to this actually do differently?
3 things. First, run your single agent baseline before you architect anything. Not a toy baseline, a genuine measurement on your actual task. If it's above 45%, you probably don't need multi-agent coordination. Second, if you do build multi-agent, use model diversity rather than agent count as your primary design variable. A 2-model system with genuinely different architectures is more valuable than a 5-agent system running the same model. Third, map your task's dependency structure before choosing a topology. Is it parallelizable, sequential? What are the ordering dependencies? The architecture should reflect the task structure, not default to whatever the framework's default configuration is.
I'd add a fourth, which is measure per step reliability and do the compounding math before you deploy. The gap between 97% and 99.5% per step sounds small, and the end-to-end difference is 21 percentage points on a 10-step workflow.
That's the one that will catch teams by surprise in production. The benchmark numbers look fine, the per-step reliability looks fine, and then the system fails 1 in 4 times at scale and nobody understands why. The math is not intuitive until you work through it explicitly.
The deeper implication here, and I think this is what Daniel is really gesturing at with his question about agent swarms, is that the vision of emergent coordination at scale may just not be how capable AI systems end up working. The research is pointing towards something more deliberate and more engineered.
The swarm vision assumed that coordination would emerge from scale the way capabilities emerge from scale in training. But coordination isn't an emergent property of agent count, it's an engineered property of task decomposition, topology, and verification. You can't throw agents at a problem and expect coordination to emerge, you have to design it. And once you accept that, the question stops being how many agents, and starts being what is the minimum coordination structure that solves this specific problem. That's a much more tractable engineering question, and the research is now giving us the tools to answer it.
Good framing to end on. Minimum viable coordination rather than maximum visible complexity.
That should be on a poster somewhere in every AI engineering team's office.
All right. Real practical stuff in this one. If you're building agentic systems, this research is directly relevant to decisions you're making right now. Big thanks to our producer, Hilbert Flumingtop, for keeping the machine running. And thanks to Modal for the GPU credits that make this whole pipeline possible. This has been My Weird Prompts. If you haven't followed us on Spotify yet, we're there. Search My Weird Prompts and hit follow so you don't miss an episode.
See you next time.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox.
Thanks for listening to our show. My weird prompts where our thoughts go from slow takes to facts on cue. We change and